In this video, I hope to introduce you to the mean value theorem. Below the link to the video, you see a drawing process that I'd like you to go on and start. And then we'll finish that drawing together. The goal being is that this sketch we're starting independently of each other will give us all different pictures, but with the same conclusion that will end with a statement of the mean value theorem. Okay. So I'm going to get started on that process now, and then there'll be a few steps at the end that you'll need to add to your picture. But the first thing I ask you to do is draw a y and x axis and to label two x values. The first one's going to be called A and the second one's going to be called B. And you can place those literally anywhere you wanted to on the x axis. I'll just choose one spot to the left of the y axis and one spot to the right. Then our job was to plot 2 points, one with an x-coordinate at A and one with an x-coordinate at B. And you could plot those anywhere too, as long as I have the correct x-coordinates. Our goal in the end is to draw a function y equals f of x that connects those 2 points in a special way. So we went on and labeled the y-axis values at these points using function notation. And now I'm supposed to draw a function that connects these 2 points, that is continuous on the closed interval, so no hops, skips, breaks, or jumps, including at the endpoints, and then differentiable on the interior, which means no sharp points. So I just need to connect these 2 dots in some way so that I avoid places where my derivative is undefined and where I avoid things that are not continuous. All of our pictures could look different. In fact, one possibility would just be draw a straight line. I would ask that you do something more creative just for fun. And there's my function, y equals f of x. Continuous on the closed interval and differentiable everywhere on the open interval. The last step of your drawing process that was posted below the link was to draw the secant line that goes between the points at A and B. I'm going to use a straight edge later in the video. If you don't have a straight edge with you, you'll find one handy, and just a folded up piece of paper would work. But now that I've drawn that secant line, I want to remind you about the slope of the secant line. The slope is the average rate of change on the interval a comma b. And we even could calculate that slope using the notation we've chosen. F of b minus f of a all over b minus a. Change in y over change in x. That would give us the average rate of change. So let's complete our sketch now. So here's the last step. Take that straight edge or folded up piece of paper and lie it along your secant line. What I want to do is move the straight edge so that I find a tangent line that's parallel to the secant line. So I never want to change the slope of the straight edge. I want to leave it parallel. Parallel lines have slopes that are the same. And I want to find a spot where my straight edge just touches the function in one spot. Well, one spot near that point of intersection at least. So I'm just going to scoot this up, and I think I already see it. I think there's a spot right here where if I draw a tangent line, it will be parallel to my secant line. And I think if you're watching this video and saying, well, Bob, I agree with that, you might find another spot down here. What I'd like you to do now is go on and pause the video and try to do this on your sketch. Find any place where you can find a tangent line parallel to the secant line you've drawn. Okay, so now that we have these tangent lines drawn, let's remember that when talking about a tangent line, the slope is an instantaneous rate of change at a particular point, and I'll call that point C. And in fact, I'll label this one C. But more than that, the slope of that secant line is the first derivative evaluated at that x value. And so I'm calling that one C. I could call this one C if I wanted to. I could call that one C1 and this one C2. But I want to focus on just one of them because maybe in your diagram you only found one of them. Okay, well the big deal is this line's parallel to that line, which means their slopes are equal. That f prime of C is equal to f of B minus f of A all over B minus A. And this is what the mean value theorem says, that if I have a function that is continuous on the closed interval, differentiable on the open interval, there is at least one value C between A and B where the first derivative is equal to the slope of that secant line. There's at least one spot where the instantaneous rate of change is equal to the average rate of change. This is what the mean value theorem says. In the next video, I'll write the mean value theorem down formally and we'll do an example.